Edexcel Core Pure, second order differential equations 1, homogeneous equations. The auxiliary equation method for first order differential equations. In this video we will be considering second order linear differential equations with constant coefficients, such as this example here. A d to y by dx squared plus b dy by dx plus cy equals f of x. The order of is the highest derivative which is used. Linear is because the y term and its derivatives all have a power 1, and the constant coefficients are fairly obviously a, b and c. If the function f of x on the right hand side is 0, then we say the differential equation is homogeneous, and if the function f of x is not 0 on the right hand side, then we say the equation is non-homogeneous. So before we look at second order differential equations, we're going to look at methods used for first order linear homogeneous differential equations of the form dy by dx plus ky equals 0. We already know that this can be solved by separation of variables to give the solution y equals constant a e to the minus kx. Knowing that this is the form of the solution for any first order differential equation of this type leads to an alternative method for solving, which does not involve separation of variables or integration. So here we have the first order linear differential equation 3 dy by dx plus 2y equals 0. So this time I'm going to try y equals a e to the mx as my potential general solution, in which case dy by dx would be a m e to the mx, a little chain rule there, and if we substitute these two into the differential equation, we get 3 times the first derivative plus twice y has to add up to 0. A cancels, e to the mx cancels, and notice that we already can see that we are not using separation of variables. We're using a different approach to trying to find the solution. So we're left with 3m plus 2 equals 0, in which case m equals minus 2/3. And this equation that we solved here is called the auxiliary equation, and we're going to be using the auxiliary equation approach extensively in future videos. So if y equals a e to the mx, and we've just found m, that means that y should be a e to the minus 2/3 of x, and this is the general solution that we've been looking for. And we've found that general solution without using separation of variables or integration. Quite a nice thing for you to try and do now is to take this solution, find dy by dx and substitute y and dy by dx back into the differential equation to verify that it is a valid solution and that everything adds up to 0. So always try and write down the function of y that you are trying, and make sure that you clearly have the auxiliary equation written down at some point. Solve the auxiliary equation for m and use it to write down your general solution. So summarising things and looking at things more generally, now we're looking at a dy by dx plus by equals 0. So if we try y equals a e to the mx, then that will produce this auxiliary equation. am plus b is 0. We can solve for m, and we can use that to then write down our general solution. So in this case it would be y equals a e to the minus b over ax. That would be our general solution in this particular scenario. This idea will be extended to second order differential equations in some separate videos to come. In the next video we're going to be looking at auxiliary equation method for second order differential equations.